Welcome everyone. In this video we are going to derive the formula for the force of buoyancy. Now what is the force of buoyancy? Buoyancy. You might be asking. Well, this is just the net force exerted on an object by a fluid. So what are fluids? Gases and liquids are fluids. So as I said, we will find the formula for the force of buoyancy. To do that, I will draw a container first, perhaps like so. And inside of it, there will be some kind of liquid, some kind of fluid, but it is in fact a liquid. Because a gas, well, it would probably evaporate. So if we have this, and if we have an object, and for simplicity, I will choose a cube as our object. So all surfaces will be the same for our object. This is the object that we have. Now, I want to find the net force on this object, which will be the force of buoyancy. A couple of variables that we can use. One of them is the rho, the density of the fluid. The other one is G, the gravitational field strength. It is downwards. And what else? Well, maybe we can also say the volume of the object is given. But even if it isn't given, you have perhaps the mass, the density, you can figure it out. Cool. Let me even erase this. So here we go. I will focus on the front side of the front surface of the object, I mean. So here is the front surface of the object, excuse me. Now, on the right side, from the right side, there will be a force acting on the object, right? To the right surface, there will be a force. And also to the left surface, there will be another force. Now, since the depth is the same for the right and left surfaces, the forces are the same as well. Because pressure is force divided by area by definition, which means force is pressure times area. And what is pressure for a liquid? Well, it is rho GH times A we will have. So this is rho GH. And in a video that was a long time ago, it was the second video of this channel, I believe, I proved this. So you can access that from the cards right now and also from the descriptions part. So my argument was like this. Since the height is the same for the right and the left surfaces, the forces are the same. Which means if this is F1, this is F2, F1 equals F2. So there is no net force from the right or left. Also, if we consider the direction that is towards the board and out of the board, the depth is still the same. So the forces cancel out each other as well. The only net force, the force that won't be cancelled, will be vertical. Because look at this. If a force, so let's do it with red. If force F3 acts like this and force F4 acts like this, force F3 and force F4 will not be equal to one another. How do we know this? We know this because the heights are different. The depth is not the same, which means the force should not be the same. And you can notice that F3 will be greater than F4 because it has a greater depth. Alright? And force is proportional with depth, as we can see it here. I use H to refer to depth. Even though it reminds you height, it isn't height. Because, notice, height is measured from the bottom to the top, but depth is measured from the top to the bottom. There is a very important difference. So we have this, and this means the force of buoyancy, if I call it FB, will be F3 minus F4. And we already see that it will be upwards. So the force of buoyancy will be upwards. Now we are looking for its magnitude. We have the direction. What about the magnitude? This is equal to. What is F3? Well, F3 will be rho g h3 times A, the surface area that it acts on, and it is going to be acting on the bottom area, right? Minus rho g h4, and what is the area that force 4 acts on? Well, it is again going to be A, because we chose a cube, so that the top and bottom areas, in fact all surface areas, are the same. Continuing on from this part, we have rho g. If I factor out A, I will have h3 minus h4. Now I want to label h3 and h4 on the diagram, because this will give us an interesting result. If I have it, if I name this h4, which it is the depth of the top of the object, well then this part will be h3, and their difference, which is this factor right here, their difference is going to be this, which is simply the length of one side of our cube. I can call that L. So h3 minus h4 will give us L, the length of the side of the cube, which means this is equal to rho g AL. What do you call A times L in this case? Well, it is the surface area times the side. So it is kind of the surface area times the height. So it should give the volume. This is rho GV. And which volume? Well, the volume of the object. Alright, so this is the formula, by the way. The force of buoyancy is equal to rho, the density of the fluid, not the density of the object, the density of the fluid, times the gravitational field strength, times V, the volume of the object. Now, this was a very quick derivation, but I want to highlight two important things which may not be obvious from this derivation. So, what I want to highlight first, let me write one here, is that the volume is the amount of volume that is inside the fluid. So this is Vn. Okay, if perhaps, let's say we have an object like this, then in this case we are interested in this volume, the amount that is inside. And you can convince yourself that this is correct by considering a similar setup and trying to find the net force again. So this will be the H inside. When you multiply with A, it will give you the volume inside. Okay? So this volume is in fact volume inside. That was number one. And number two, another way of saying the force of buoyancy, representing it, is by saying it will equal the weight of the displaced fluid. Weight of the displaced fluid. How does that work? You might be asking, how does it work? Well, it works like this. We have rho, which is the density of the fluid. We have V inside, which is the volume of the object that is inside the fluid. So it is also the volume of the displaced amount of fluid. And we have rho times V. Well, that is going to give us, by definition, the mass. The mass of the displaced fluid. And fluid, we can call it. And we have an additional G factor. So we have M fluid times G, which is the weight of the displaced fluid. Okay, this is, as I said, another way of talking about the force of buoyancy. And this one is, in fact, a lot more important in my opinion. Anyways, I hope this video was helpful. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.